So question number 5 says an electromagnetic wave in a vacuum has a wavelength of 8.4 times 10 to the power of minus 6 meters. State the name of the principal region of the electromagnetic spectrum for the wave. This is obviously infrared radiation. It is a must that you must know all electromagnetic waves, 7 of them, and their corresponding wavelengths, the range of their wavelengths. So this is infrared radiation. Okay, calculate the frequency in terahertz of the wave. So first things first, we have to calculate the frequency. So remember the wave equation says V is equal to F lambda. So that's the one equation in waves that contain wave frequency. Then another equation which contains frequency is 1 over T. Since we are not given period, we are not going to use this equation. We are going to use this one because we are at least given wavelength. So the question is, who is the speed? Since it's an electromagnetic wave, the speed is the speed of light. So we have wavelength, so frequency is easy to find. So frequency is equals to speed of the wave over wavelength. Then we go further and then we say speed of electromagnetic waves is 3 times 10 to the power of 8 divided by the wavelength which you are given, 8.4 times 10 to the power of minus 6. So it's 8.4 times 10 to the power of minus 6, which will give us our answer is 3.6 times 10 to the power of 13 times 10 to the power of 13. But this answer will be in hertz. They want the answer in terahertz. So how do you convert it to terahertz? Remember, tera is the power of 10 of tera is 10 to the power of 12. So if you want to add tera, it's a law that if we want to add tera, we divide by the power of 10. So it's 3.6 times 10 to the power of 13. The moment we add tera here, automatically we must also divide by the power of 10 of tera, which is so that mathematically we have cancelled out, because it's more like you are saying if your answer was 5 and then you multiply by 2 and then you divide by 2, so this multiplication by 2 is cancelled out by the division by 2. So here it's more like we're multiplying by tera at the numerator, and then we divide by 10 to the power of 12 at the denominator. So they more or less cancel each other. So ultimately the answer will become 3.6 times 10 times 10, which becomes actually 36 terahertz. So we write our answer in the space provided. So the answer is 36 terahertz. Then we go to the next one. An arrangement that uses a double slit to demonstrate the interference of light from a laser is shown. So we have a double slit experiment there. It is obvious that this 2.8 here in the formula that says X, the fringe separation, is equals to lambda D over A. It is obvious that the D will be 2.8. A is labeled there. Then when we read the question, we'll find lambda, I believe. The light from the laser has a wavelength of 6.2 times 10 to the power of minus 7. This is our lambda, and is incident normally on the slits. The separation of the slits is A. The slits and screen are parallel and separated by a distance of 2.8 meters, which is capital letter D. An interference pattern of bright fringes and dark fringes is formed on the screen. Okay, the distance. So an interference pattern will be formed on this screen. This you must know. There's a screen here. An interference pattern of dark and bright fringes is formed. We explained this one, but bright fringes are formed because of constructive interference. Dark fringes are formed because of destructive interference. So an interference pattern is formed on that screen. Dark and bright fringes, destructive and constructive interference. Okay, so then we proceed an interference pattern of bright fringes and dark fringes is formed on the screen. The distance on the screen across 8 bright fringes is 22 millimeters. Okay, so I think we must be aware of this. So these regions here are representing the bright fringes. Bright fringes where constructive interference is happening. So the distance between from here to the here 8 bright fringes is what? Is 22 millimeters. Now to stay here a little bit, we would say the distance x in that equation that I wrote earlier is actually the distance from the center of a bright fringe to the center of the next bright fringe. That's the distance x. So if we are given that the distance between 28 bright fringes is 22, if we want to find x, we would have to divide 22 by 8. Then that will give us x. Okay, so let's go here, down here. The light waves emerging from the two slits are coherent. That's what is meant by coherent. You must know, as a matter of fact, this one. Coherent simply means that they've got a constant phase difference. There's no need for conjecture or even worrying here. Constant phase difference. That's what coherence means. Constant phase difference. Calculate the separation A of the slits. That's the next question. So you are supposed to find A, but how do you find A? You must write the equation first. X is equals to lambda D over A. So in other words, A is equals to lambda D over X. So now we proceed with the question. Lambda is given, lambda the wavelength, and D is 2.8, but lambda is 6.2 times 10 to the power of minus 7. So we will write lambda 6.2 times 10 to the power of minus 7. D is 2.8. Then X, the fringe separation, it's remember it's in millimeters, but before we put it in millimeters, we must divide it by 8. Then we multiply by 10 to the power of minus 3 to convert it to 2 meters. So when you do this, we'll find that our A by calculation will be 6.3 times 10 to the power of minus 4. 6.3 times 10 to the power of minus 4. So we get our answer here. A is 6.3 times 10 to the power of minus 4. That's our A, 6.3 times 10 to the power of minus 4. So then we go to the next part of the question. The fringe P is the central bright fringe of the interference pattern in B. The fringe P is the central bright fringe. This fringe P is at the center, the central bright fringe. Central bright fringe usually happens somewhere here, such that the distance from here to here, sorry that it is curved a bit, but the distance, let me zoom in a bit, the distance from here to here is refusing to make it like that, and the distance from here to here are equal. That's the central bright fringe P. So they say the fringe P is the central bright fringe of the interference pattern B in B. Find the fringe Q and R are the nearest dark fringe and the nearest bright fringe respectively to the right of the fringe P as shown. Calculate the distances, the difference in the distances or the path difference from each slit to the center of fringe Q. So we want to find the distance to the center of fringe Q. So fringe Q is the first dark fringe after the bright fringe. The first dark fringe after the bright fringe. We are looking for its path difference, the path difference to get there. So we need the formula of the path difference, and you must know the formula of the path difference for destructive interference, starting with the first dark fringe. But since this is destructive interference, because it's a dark fringe, path difference, you write it as path difference is equal to n plus half lambda, where n is equal to 0, 1, 2, 3, and you continue like that. So that's the path difference when there is destructive interference when you produce a dark fringe. When you produce a dark fringe is 0 due to destructive interference. So the path difference for destructive interference is this one. So, and since it is the very first, dark fringe, then for it n will be equal to 0. So in other words, we'll be saying if n is 0, then it's 0 plus half lambda, then which is equals to half times lambda. But lambda is the wavelength, which is 6.2 times 10 to the power of minus 7. This becomes 3.1 times 10 to the power of minus 7. So in the space for the answer we write 3.1 times 10 to the power of minus 7. That is the path difference of the light to form a dark fringe at Q, because that's the very first dark fringe, so the destructive interference has happened there. Then the question asks you for the set the first difference between the light waves meeting at the center of fringe R. Now, if you consider fringe R, now fringe R is different. Fringe R is the second bright fringe from the central bright fringe. So now, if it is about finding first difference, remember this first difference is for the double slit experiment. In this case, it's not just any first difference. It's not first difference on a single wave which is moving on its own. It's first difference. No, it's not first difference of the particles on a wave. No, it's first difference of the particles arriving from the slits, of the waves arriving from the slits to meet to form a bright fringe. So first difference in this particular question, you should not confuse this first difference to any other first difference. This first difference in this particular question will be equal to, again, since it's for constructive interference, it will be n 3/6. You can swap 360 for 2 pi, depending on whether the answer is needed in degrees or in radians. Where n equals to 0, 1, 2, 3, continuously like that. That is the first difference for constructive interference. For constructive interference, first difference for constructive interference in the double slit experiment. So in this case, n will be 0 for the first one, the central bright fringe. N will be 0, so for the central bright fringe, and then for the second, which is at R, which is not the central bright fringe, n will be 1. So we will be saying 1 times 360 here to give us 360 degrees. So our answer will be 360 here. So